Okay, right. So let's start. Two of you on, Jiaming and Jason. Any questions? Any questions for me? Huh? Jason? Jiaming? You want me to go over anything that we've covered so far? Hmm? Yeah. Anything you want me to go over? I can go over them if you want to, but I need to know what is it that you want to go over. Hmm? Yeah, there are three of you now. Yeah, please do ask me questions here. Otherwise, I do not know what you all want. And then we're just looking at the screen. Questions? Slow start now today. No questions. Anything? You can ask me anything, you know, please. Can we go through the important points of last lecture? Sure. Okay, let me bring up the last lecture first, okay? So the last lecture we had was lecture 8, if I'm not mistaken. Correct? Right? Am I correct? Chapter 8. Okay. So in chapter 8, we basically introduced the general form of the first order and second order systems. Okay, so we had the general form of the first and second order systems. And then we looked at what would be the response of these two types of systems for two types of inputs. Okay, an input which is an impulse, in which case we call it an impulse response, and an input which is a step input. All right, and then we call that a step response. Okay, so the general form for the first order, this pen also dry up. First order system, the general form look like this. I use tau or T here. Let me see first. I use tau. I think your notes I use T. Let me use tau. Tau S plus 1. That was the first order. Okay. Let me put back my camera. Okay, that was the first order. And then for the second order system, we have the general form of K omega n squared over S squared plus 2 zeta omega n S plus omega n squared. That was our second order. All right, where zeta is the damping ratio. Omega n is the undamped. Okay, undamped natural frequency. Okay, and K is the steady state gain. So these were the two general forms of transfer functions for the first order and second order system. And we gave you examples of this. So for the first order, the example was the RC circuit. Okay. For the second order, we have the example of the parallel LRC circuit. So we have both examples. Okay. We had both of them. All right. And these were shown here. Okay. The RC circuit. All right. Yeah, we didn't show it here. There, the LRC second order. Okay. All right. So in each of this case, we see that each of these have their own poles, because the poles will determine the behavior of the system. Recall that when you look at the output of the system, it is GS times XS, and X, right? XS is the input, GS is the transfer function of the system, and YS is the output. Okay, we had this. All right. So we also said that when we look at the output of the system, this leads to a YT, where we have a transient part and a steady state part. All right, this we did in chapter 7. All right, and the transient part is dependent on the system pose, whereas the steady state part is dependent on the input pose. So knowing the pose is important in that case. All right, knowing the pose are important. Okay, so if you look at these two transfer functions, the one for the first order and the one for the second order, each of them have their own pose. All right, so for the first order, so this is for the first order. What is the system pole? It will be minus 1 over tau. 1 over tau. In other words, what is the root of the denominator? The root of the denominator is when that whole function there, which is tau s plus 1, becomes 0. So what's the value of s? S will be minus 1 over tau. All right. In the second order system, okay, what are the poles? So to find the poles, we use the formula of minus b. You know, we use this minus b plus or minus square root of b squared minus 4ac over 2a. Right? We use this formula, and if we use this formula, the poles that we obtain is this guy here. All right, over here. So be minus zeta omega n plus or minus omega n square root of zeta squared minus 1. So these are the poles of the second order system. So this will define how the transient behavior looks like for the output. All right, for the system poles. The input pole, of course, will depend on the input. If the input is a impulse, then the input pole will be 1. 0, 0, okay? There is no input pole. On the other hand, if the input pole is a step function, right? Then the input pole will be s equals to 0. All right, so those are the conditions that we are looking at. Right, so this was the basic foundation of looking at the responses. Okay, so when we look at the first order is straightforward, first order. When we look at the second order, we find that there are 4 cases depending on the value of zeta. 4 cases, all right? If zeta is less than 1, you will get a negative square root here, right? If zeta is less than 1, zeta squared will also be less than 1. Less than 1 minus 1, of course, you got a negative value. Okay, so there were 4 cases. So case 1 was when zeta is less than 1. Okay, so when zeta is less than 1, we have complex conjugate. Yeah, first order is 1 minus 1 over tau. Yes, over here. Yeah, first order is over here. For second order, when zeta is less than 1, the poles become minus zeta omega n plus or minus. This becomes a negative square root, which means there's a j. J omega n square root of 1 minus zeta squared. So this was the case of what we call underdamped. Okay, now when zeta is equal to 1, this becomes 0. The square root becomes 0. All right, and then your poles will be repeated poles. Because don't forget there are 2 poles there. Repeated negative real numbers. When zeta is greater than 1, so this is what we call critically damped. When zeta is greater than 1, we just have this minus zeta omega n plus or minus omega n square root of zeta squared minus 1. So we call this overdamped. And finally, when zeta equals to 0, then this becomes 0. Okay, you just get this guy, square root of -1. It just becomes plus or minus j omega n. And this is no damping. All right, so those are the 4 cases for second order systems. Any questions up to this point? Any questions? Huh? No questions up to this point? All right, we have Ming Xiang who also joined us. Thanks coming. All right, so Ming Xiang, we're just going through a revision of what we went through in the last chapter, in the last lecture on Monday. All right, so I'm just going through the basics first. All right, so what is important now is that we need to recognize what is the general form of a first order system, what is the general form of the transfer function of the second order system. We learned from the previous chapters that the output has a transient part and a steady state part. The transient part is dependent on the system poles. The steady state part is dependent on the input poles. All right, so when we look at the transient part, for the first order system, the input pole is -1 over tau based on this GS up here. For the second order system, the roots of the denominator over here, denominator is s squared plus 2 zeta omega n s plus omega n squared. The roots of this is given by this thing, this formula here, okay, which are obtained by applying this minus b plus or minus square root of b squared minus 4ac. And I hope all of you know this. Huh? So in this case, what is A? A is 1 because it's as squared. A is 1. What is B? B is 2 zeta omega n. And what is C? C is omega n squared. All right, let me just write it down here. A is 1, B is 2 zeta omega n, and C is omega n squared. You apply it into this formula, you get your roots, which is given by this formula here. All right, so those are your poles. And we found that the poles, there will be 4, based on these poles, there'll be 4 cases depending on the value of the damping ratio zeta. And that's what I put down here. Zeta less than 1, these are the poles, and it is the underdamped situation. Zeta equals to 1, you have real repeated poles, okay, and that's critically damped. Zeta greater than 1, you have real poles, okay, overdamped situation, and zeta 0 is imaginary poles, which is no damping. Okay, right. So now with this, we can now apply all this for the case of an input, which is a delta function, which is an input impulse, and also for the case when the input is a step function. So let's take the input as a delta function first. Okay. So the first case we will talk about impulse response. So in impulse response, in this case, we have xt is delta t. That's your impulse, your input, right? Which means that xs is just 1. Right? So we know that the output in the Laplace domain ys is gs times xs. Right? And xs is 1. So in that case, it's just equals to gs. Because xs is 1. All right? So now depending on first order or second order, you substitute inside here. Right? So for first order, then your ys is just this gs, and gs we found was 1 over tau s plus 1. That was first order. Right? So from there, we can see that the output YT will be, okay, we can put this in this formula, it's better, 1 over tau into 1 over S plus 1 over tau. Okay, we can put it this way. So you can see there's a shift in S here. So YT is 1 over tau e to the minus T over tau UT. That is your output. Okay, and we draw it up, we showed you that waveform over there, which is this guy. Okay, so in this case, I use 1 here, K is 1, okay, but in this notes here, K, the numerator is K. So in this case, in my example here, K is 1. So if you want, I can put K here as well. K here as well. K here as well. So that was the first order. All right. For the second order, we have those four cases, depending on zeta. All right. So for the second order, when we go through these operations, you remember when we try to derive YT, remember we have these 4 steps. Step 1 is obtain the differential equation. Step 2, you get the Laplace. Step 3, you do the partial factors to find the capital A's. And step 4 is to do the inverse Laplace. I won't go through the whole detailed derivation, just to summarize it for you guys. So in the second order, you do the same thing. In the second order, okay, you do the same thing. So now apply this one, all right? Okay, your YS, again, is your GS times XS. And GS now is K omega n squared over S squared plus 2 zeta omega ns plus omega n squared. That is your GS. And your XS is the step function, which is 1 over S. All right, so after this, you will do a factorization. Okay, now you don't have to prove all this. You're not required to prove all this. You're only required to understand how to use it, that's all, the final result. All right, so if you do your factorization and your inverse Laplace transform, what you will get is what you have in your formula sheet here. Okay, here. So those are your 4 cases here. So I'm just going to summarize those 4 cases. All right, so when you do this, okay, the result of YT depends on those 4 cases. So let's say if zeta is less than, okay, the 4 cases here is greater than, equal, less than, and no damping. So if zeta is greater than 1, we have the overdamp case. All right, and if you go through those 4 steps, those 4 steps, remember, step 1 is differential equation, step 2 Laplace, step 3 factorize, step 4 inverse. Okay, your answer will come up to be the following, which is, okay, it's a bit hard for me to see. Let me expand it so that I can see. My eyes not so good. Okay, so your if you do this, your YT will come out to be the following. All right, which is K over tau, because I changed everything to tau, E K, oh, sorry, this is the first order. YT will be K1 e to the minus P1t. We'll tell you what is P1t and P2t, plus K2 e to the minus P2t, where P1 is omega zeta omega n plus omega n square root of zeta squared minus 1, and P2 is zeta omega n minus omega n square root of zeta squared minus 1. So those are your P1 and your P2. Okay, so similarly, if you do it for the critically damped case, zeta equals to 1. If you go through the derivation, you will get this guy here, which is YT will be K omega n squared E to minus omega nt. All right. Okay, of course you have to multiply by UT. I got no space to put that. Huh? Okay, this whole thing times UT. Okay, so this whole thing times UT. All right. The third case will be when it is under damped, less than 1. Okay, of course it has to be a positive value. Then your YT will be the following: K omega n squared over omega d e to the minus sigma t sine omega d t, the whole thing again multiplied by ut. Okay, and the relationship between omega d and omega n is omega n square root of 1 minus zeta squared. Okay, and finally we have zeta equals to 0, no damping. Then yt becomes k omega n sine of omega nt, again whole thing multiplied by ut. Okay, so that was for the first order system. All right, let me shrink it so that I can. So these are the 4 cases, right? The 4 cases. All right, under damped, you get this output. Critically damped, you get this output. Over damped, you get the first one. Critically damped, you get the second one. Under damped, you get the third one. And no damping, you get the fourth one. All right, those are the 4. And it's all in the formula sheet that we have provided. All right, and that's going. So as I said, if you go through those derivations, step 1, step 2, step 3, step 4, this is the result. Okay, so in this case, it is for the, okay, when for the case when the input is an impulse, the input is an impulse. Any question? Okay, of course, in the lecture notes, we show you the shape of all this. We draw the graph for YT, right? As you can see here, right? So YT first order, we graph, throw it. Then this is for the overdamp, this for the underdamp, and this is for the critically damped, and finally no damping. So those are the 4 diagrams. Any question? So we can do the same thing for step. When the input is a step, go through the same process again. All right, as I said again, you do not need to know how to derive this, but you need to know how to use it. And I'll explain why, how this is being used when we present questions to you later. Okay, so but that's the theory. This is the theory part. Questions? Okay, so far, everyone? Okay? Okay, good. All right, so I'm actually trying to summarize what are the key things that you need to learn, you need to understand from Monday's lecture. Okay, these are the key things. Okay, so this is the case when the input is an impulse. So we can do the same thing again. When the case when the input is a step function. All right, let's summarize that. Okay. Okay, so now we have step response. Okay, we look at step response. So in this case, your input is a UT because your input is a step, which means that your XS is 1 over S. And so your output, which is GS times XS, will be GS times 1 over S. Okay, and GS of course will depend on first order or second order lah. Huh? All right, so we do the same thing. So for first order, all right, then your YS will be K over tau S plus 1, which is your GS, times 1 over S. And again, you can factorize it and so on. All right, and if you do that, okay, let me put this back here. If you do that, you will find that your step output, YT, will be this guy. You see, so small. K over tau, e to the minus t over tau. Okay, ut. This will be your output, which is this guy here. Oh, is it k over tau? No, sorry, wrong one. Which is this one? I wrote the wrong one. Okay, it's the second one, which is your YT will be K. I can't see. K into 1 minus e to the minus t over tau ut. Okay, so that's for the first order. Right? Similarly, for the second order, you have your 4 cases: over dam, critically damped, under dam, no damping. So you will have different YT output. Okay, different YT output when you go through those 4 steps. Right? 4 steps. Okay, so if that is the case, let's write down the 4 steps. Not the 4 steps, but the result of those 4 steps. So the first one is for the overdam case, zeta greater than 1. All right, if zeta greater than 1, your output will be this thing here. Very hard for me to see. Bracket K minus K1 over K2. We will tell you what's K1 and K2. Let me see. K1 over P1, not K2. P1 here. Okay, P1. E to the minus P1T. Okay, minus K2. K2 over P2, e to the minus P2T, and the whole thing UT, where P1 and P2 is what we see in the sheet here. P1 will be, P1 is omega n into, is it now? Then, no, I can't see. P1 is omega zeta plus, what is it? Omega n square root of zeta squared minus 1, and P2 is omega n zeta minus omega n square root of zeta squared minus 1. So that's the case for overdam. All right, and that's the expression for K1 and K2 too, which you see in the formula sheet. All right, over here, K1 and K2. So in the case of critically damped, zeta equals to 1. Okay, then this is your YT, don't forget. So YT will be the following. Okay, critically damped, you have K into, okay, I can't see. 1 minus e to the minus 1 minus e to the minus omega nt e to the minus omega nt minus omega n e to the minus omega nt, the minus omega nt. okay, and the whole thing ut. So this is for the critically damped. Okay, then the next one is when zeta is less than 1, then yt will be equal to, let me blow it up a bit so that's easy for me to see. Right now it's very hard for me to see. Okay, so this is for critically damped, and now we have under damped. We see that it is K into 1 minus omega n over omega d e to the minus zeta t, sigma t sine of omega d plus phi, okay, ut, where sigma is zeta omega n and omega d is omega n square root of 1 minus zeta squared, and phi is what you see here in the formula. What is phi now? All right, fine, okay. There. Phi is arctangent of omega d, tan minus 1 of omega d over sigma. That is fine. All right, and finally we have no damping equals to 0. Then yt will be just this last expression, k into 1 minus cos of omega nt, omega nt, okay, ut. So those are your 4 cases for the step function. All right, so each of these, if you go through the derivation, will be these 4 steps, right? These 4 steps: differential equation, Laplace transform, factorize, inverse Laplace transform, and you will get all these respective yt's. Okay, yeah, this pen is a bit too thin. Hold on. I don't have a thick pen. All right, pen is a bit too thin. Thanks. Let me see. Okay. Yeah, I use this other one. This one is thicker. Okay. Okay. All right, those are your 4 cases. All right, and again, we showed you the diagrams. We showed you the diagrams. All right, as you can see inside your lecture notes here. Okay, so this is the first order, given a step input. Okay, so this is second order with zeta greater than 1, as you can see here. This is the under dam. Okay, this is the critically damped, and this is the no damping. So those are the 4 cases. Okay, I'll talk about some of the characteristics afterwards, but basically that is what it is. Those are your 4 cases. Any questions at this point in time? Any questions? Yeah. All right. So let's look at some of these characteristics. Okay, let's look at some of these characteristics. Okay, so let's rewind a little bit. Recall that we mentioned earlier about these 4 cases here. All right, depending on the zeta for second order. Now, what that means is that we got to know where we should understand where are these poles. Where are these poles? All right. So if you look at this, right, this thing, let us see where the location of the poles. Okay. So the first one is for the under damped case, we have complex conjugate poles. So if you draw it, this is real, this is imaginary. So for your complex conjugate poles, you'll be up here and down here. and this is minus zeta omega n. All right, and up here will be this guy here. All right, j of omega n square root of that. But that guy is actually omega d, is j omega d and minus j omega d. So this is for the under dam. Okay, where omega d equals to omega n square root of 1 minus zeta squared. That's where are the poles for the under dam case. Okay, in addition to that, if I draw the diagonal over here, this diagonal over here, that is omega n. And if I look at the angle over here, which I call beta, okay, zeta equals to cos beta. These are the relationships. Cos beta. All right. So we said that depending on the angle beta, the extreme cases will be when beta is 90 degrees. If beta is 90 degrees, then this goes all the way up to here, to the y-axis, in which case cos of 90 degrees is 0. So when beta equals to 90 degrees, all right, zeta is 0 because cos of 90 degrees is 0. When beta is 0 degrees, then zeta cos of 0 is 1. Those are your extreme cases. Zeta equals to 0, what does it mean? No damping? No damping. Zeta equals to 1 means critically damped. All right, so this is the case for the under dam situation. All right, this is under dam. Okay, so we can do the same for the others. Right, critically damped will be the following: real, imaginary. So critically damped is repeated poles at here, minus zeta omega n. There'll be 2 of them here. All right, 2 of them. That is critically. All right, then the one is over damped. So over damped, all right, again, if you draw it, there are 2 rail poles at plus and minus this. 2 rail poles, one here and one here, say. Okay, one is when you have, the first one will be minus zeta omega n, all right, plus omega n root of zeta squared minus 1. That's the first one. The second one will be minus zeta omega n minus omega n root of zeta squared minus 1. So this is for this guy. This is for this guy. Okay, so that is the over damped case. That's where your poles are. And finally, when the no damping case, no damping, as you can see, is just plus or minus j omega n. So in this case, it's just on the imaginary axis. So this is no damping. So if you draw it, real, imaginary, so it will be at here and here. So the 2 places will be j omega n minus j omega n. So those are where your poles are. Okay. Any questions? So we're just looking at the characteristics of some of this, all these formulations that we have done. Any questions at this point? Okay, all right. Is it clearer to all of you right now when I go through this recap? I really don't have any response here. I don't know whether I'm going the right direction or not. Can some of you say something? Okay, at least I get some response, because I'm not sure if this is what you want me to cover, you see. Okay, all right. So this is where the poles are located. Where the poles are located, right? Okay. Now, the other thing that we also did was to look at the response for the integrator, right? We did the integrator here, because integrator is a special case, okay? Special case of the first order system. It's a very special case, all right? Special case. And then we said that in integrator, theoretically, your output is this guy here, which means it goes to infinity when t goes to infinity. But in most practical cases, you don't integrate till infinite time. You integrate only for a finite time. Then in that case, it flattens out. Okay, that's the main thing now, right? That was integrator. Okay, so that's the comment that I want to make, which is summarized in here. All right. Okay, that we have an integrator gain is marginally stable, and then when you integrate, you only integrate up to a certain time t. You don't integrate to infinity. So in that case, it becomes a constant. So it will not go to infinity. Okay, so that's the integrator. Okay, so now we know all these fundamental principles, fundamental principles of first order system, how we describe the transfer function for first order, how we describe the general transfer function for second order, and for second order you have the 4 cases of damping. So why do we need to know this? Okay, the reason we show you all this is that we will ask you questions. We will ask you questions relating to this type of systems and this type of inputs. And what sort of questions will you encounter? Okay, we may give you a graph, for example. All right, a graph, either of a first order system or a second order system. You know, one of those graphs that I showed just now. And we say, okay, given the graph, identify what is GS. That's what we mean by system identification, given a graph. Now, not all graphs will you be able to identify GS. What is GS? Come back to this again. Remember, GS is first order is this guy. Second order is this guy. All right. So in the first order, all right, the general form will be a formula because in this case, for the first order, I set K to 1. But the general one will be like that. K over S tau plus 1 for the first order, and K omega n squared over S squared plus. So if we say, we give you a graph, tell me what is GS. That's a question that we will ask you. We may ask you, okay? So if it's a first order graph, when we tell you it's a first order graph, what are the unknowns? K and tau. I got to figure out what is K and tau from the graph, If I give you a second order, I got to figure out what is K, what is omega n, and what is zeta. Those are the 3 parameters for second order. So we need to deduce from the graphs what these values are. And that's why we go through this whole procedure here of explaining first and second order outputs to find the YT. All right, so let me summarize that. Okay, so this you cannot see. Okay. So let me summarize that. Okay. So we know that for first order, we have GS is K over S tau plus 1. So what are the unknowns? Okay, these are the parameters that we need to find. In the second order, we are told that GS is K omega n squared over S squared plus 2 zeta omega ns plus omega n squared. So what are the unknowns? K, zeta, and omega n. These are the unknowns. We got to find what these are. Right? This is what we need to find out. Okay. Now, to help us do this, one of the things that we did was to introduce the concept of time constant. All right. And the time constant, amount of time to reach 0.632 of steady state. Right? We said that. And typically, this will have the form of E minus T over tau. You will see that in those expressions. Okay? Time to reach 0.632 of the final value. That's the time constant. Okay? So if given this information, if we say look at the first order system of a step input, say, so let's take an example of a step input. So the first order system of a step input is this guy. This is second order, sorry. Okay. Input, second order, impulse. Where is the step input? Okay, this is the step input. Okay, where is the graph? I'm just trying to, here it is. Okay, here's the graph. All right, so you see here, this is the output, right? This is the output. This is the output. So when t tends towards infinity here, e to the minus infinity is 0. So that's why the steady state is k. So you can see here, k is a steady state here. K is a steady state. All right. So we said the time constant is the amount of time it takes to reach 0.632 of the steady state. So what is 0.632? Let's say 0.633 of the steady state is down here. So you draw a horizontal line. Then after that, at the intersection here, you draw a vertical line. So that time is your tau. That is your time constant. Right? What have I done? What have I done so far? I've actually, if this graph was labeled, I can find what is K. I know what's K over here. I can also find what is tau. So I know how to derive GS here for the first order system. So that's called system identification. Okay? So you may see questions like that coming out. I give you a graph. Tell me what is GS. Go and figure out what's GS. All right. So system identification is one of the things that we are trying to provide you with the tools. These are all the tools to figure out what are the parameters of the transfer function. That's system identification. So we are doing this in the time domain, not the frequency domain, right? All the graphs are in time domain. So what about the second order system? Same thing, except that not all of them can be used. All right. So for the second order system, the one that allows us to identify K, zeta, and omega n is the case of under dam. Okay, under dam, if you look at it, it's like this. All right, so it's summarized under here. All right, looks like this. Okay, so in the under dam case, all right, in the under dam case, I'm going to print this out so I show you the procedure to find K, zeta, and omega. All right, so I'm going to revise that. Let me print this out. Just give me a minute. All right. Okay, so let me just summarize this. So basically, we are trying to do system identification here. All right, I call system identification. Okay, that means determine values of the parameters in GS. Right? That's what we are doing. All right. So for the first order, okay, we need to find, we determine K and tau from the graph, which I just explained. Right? Which I explained just now. Okay. All right. K will be the steady state value. Tau is the time constant. Tau is the time constant. And tau, how do you find? 0.632 of the final value, draw a horizontal line, then intersect, draw a vertical line. That's in the times x-axis will give you the value of tau. Okay, so K was the steady state. And this is your time constant. Right, from the graph. That's first order. Now for second order, it's a little bit more complicated. But we have to look at the equation. So this is first order. Okay. Okay, so for second order, I have to take this graph here. I'm going to take this graph here to show you. All right, this is the graph. Okay, so what I will do is this. If you look at the formula over here, back here, this is the formula of YT. Okay, this is the formula of YT. All right, over here. And you can see that it has a sine wave here, whose angular frequency is omega d. All right, which is the blue curve here. The sine wave with an angular frequency of omega d. But the amplitude of this sine wave is influenced by this term here. By this term here. And what is this term here? This term here is really the envelope, what we call the envelope, as shown by these two dotted red lines, the envelope. So over time, the envelope becomes smaller and smaller because of the exponential term here. Exponential term here. All right? That's what happens. When t tends towards infinity, e to the minus infinity is 0. And that's why it disappears. All right? So those are your clues to figure out what is k, what is omega d, what is omega n, and what is zeta. All these are the clues. So how do we do that? Okay, how do we do that? So in this diagram, the picture is a little bit hard to see, but let me redraw the steady state line here so that it's easier to see. So this is the steady state over here. Okay, can you see the line here now? Okay, I wanted to draw it not too dark so that because we're going to draw over it afterwards. Can you see it now? The steady state. All right. So these are the steps involved. Number one, let's determine omega d first. Omega d is the angular frequency of this sinusoid. So what I can do is, let me take one full cycle. So one full cycle would be say, okay, I'm going to take it from this point here to this point here. Okay, so that is one full cycle. Let me draw it over here. One full cycle. right? So that is one period. So let me call it TD. So if I know TD, I can obtain FD, right? Which is the reciprocal. And if I know FD, I can obtain omega D, because 2 pi FD is omega D. So I know omega D already from the graph. Okay, so omega D is known. Any questions here? Yes, okay. Yes or no? As I said, if you look at the formula, you can see that the sinusoid here, explain again, the sinusoid here has a frequency of omega D. Okay, what is that? Sinusoid, the sinusoid is this blue curve here, or in this case, this black curve here. So what I'm trying to find out now from this graph is what is omega D. Okay, to do that, I draw 2 points on this horizontal line that shows K, all right, and see where are the intersects for these 2 lines. So that is one full cycle of the sine wave, right? Yes, Xiaoming, is that one full cycle of the sine wave? Yes? So one full cycle means what? One period, isn't it? Okay, so that's why I call it TD. Okay, so if I know TD, I can find the frequency FD, which is 1 over TD. So I know FD, I can find omega D. Omega D is 2 pi FD. So all these are basics. So I found omega D already. Yeah, so please let me know if you all don't understand, and don't just keep quiet, because if you keep quiet, I assume you all know what is happening, you know. So I'm very happy to repeat. So don't keep quiet. The clinic is to really help you, but I can't help you if nobody says anything. Then I assume that you know what's happening. Okay, so don't be shy here, huh? All right, I can always go over the thing again. So that's omega D. So I found one value already, omega D. There's one more thing that I need to find, and that is the time constant. All right, so now you can't see on my graph here, but let me emphasize that by sketching out. Where is my red? Okay, so this is the thing that determines the envelope. Let me draw it out so that it's clearer for you to see over here. Can you see the red dotted line now? So you see that the final value is K, right? The final value over here. We know K. K is known because it's drawn here. If the graphs are all labeled, K is known. So now we know omega D. K is known, right? All right, everyone? K is known, right? So the time constant is the amount of time. Remember, time constant is e to minus t over tau. It's given by that. So it's the amount of time it takes to reach 0.632 of the final value. So the final value is K here, as you can see. This is the final value. So all I have to do now is say, okay, where is 0.632? Maybe it's here. Let's say it's here. Okay, 0.632. Let's say it's here. Okay, so this is 0.632 of K. Okay, from here, I will drop a vertical line down here. So this is my value of tau, my time constant. All right, this is my value of tau, as you can see here. So now I know tau. All right, so I know tau. So basically this is minus ET over tau is equals to E to the minus sigma T. Okay, why sigma T? Look at the equation here. E to the minus sigma T. So that means sigma is 1 over tau. And we have discovered tau already. So I know sigma. All right, I know sigma. So sigma is known. So I know sigma now. I found sigma already because sigma comes from tau. And tau is obtained from the graph. Okay, so I know three things from the graph. Number one is I can find the period TD, which leads me to FD, which leads me to omega D. So that's the first finding. The second finding, I know what is the steady state, which is given by K. Right? So the second guy. The third finding is to determine what is the time constant tau according to this method here of 0.632 of the steady state. Draw a horizontal line, intersect here, draw a vertical line. That gives me tau. So if I know tau, tau and sigma are related here, as you can see in this formula. So therefore, I know sigma. There are three things that I know now. Okay, but I still have not found zeta. I don't know yet. Omega n, I do not know yet. These are the two that are missing. Right? These are the two. Because remember, the second order system is k omega n squared over s squared plus 2 zeta omega n s plus omega n squared. That is the second order system. So I'm supposed to find out all this from the graph. Cannot understand sigma. Sigma is here. Yes. All right. So if you take our our normal way of describing the times constant is e to the minus t over tau. So 1 over tau must be sigma. There, I equate here. Okay, Om? Still no? Okay. All right. So sigma is 1 over tau based on this formulation here. All right. So as I said, we need to find all these values. So I need to still find zeta and omega n. So there are two formulas that we will need. Two formulas. Okay. The first formula is that we know that sigma is zeta omega n. This is one formula. Where do we get this? Come back to your formula sheet. Here. Under Dam system, which is this guy here. Okay. Let me here. Right under Dam, over here. Okay. Sigma is zeta omega n. Can you see here? All right. So there's one formula. The other formula is this guy here. Omega d equals to omega n square root of 1 minus. Okay, these are the two formulas. Zeta is known. Okay, so let me mark it here. Zeta is known, omega d is known. Two formulas. Can you solve for zeta and omega n now? Yes, because you got two equations. Right? So based on these two equations, this is equation 1, this is equation 2. Sigma is known. Yes, sigma we have already determined from up here. Omega d is known, we have determined from up here. Two equations. Therefore, you can solve for zeta omega n. So now you have discovered what is GS because you found all the values already. You found K, you have found omega n, and you have found zeta. So you have discovered what the system is. So that is system identification for a second order system. Okay, so let me summarize that. Okay, let me summarize that. Okay, so this is system identification for second order. Okay, step one. Okay, step one. Determine period TD. Step one. TD will lead to FD, which will lead to omega D. First thing. Number two, determine K, which is equal to steady state. This is the easy one. Right? That's the easy one, because that's where you have the steady state K. Okay? Step three is the complicated one. Determine sigma. How? Okay, so sigma, the first step is I determine the time constant tau, number one. Second is we know that sigma is 1 over tau. Okay, which I showed you just now. So now we have three values, omega d, k, and sigma. Number four, apply following equations. Okay, the first one is sigma is zeta omega n. This is equation one. The second one is omega d equals to omega n square root of 1 minus zeta squared. This is equation 2. All right. Number 5, solve for zeta and omega n from the above two equations. Okay, that's all your steps. So I summarize all the steps for you. Any questions? Is that okay? So again, we may present you with a graph, a second order system, and say, okay, for this second order system, we have applied a step input. And the output of this system is this graph. It's all labeled. Y-axis is labeled, x-axis is labeled. X-axis is the time. Determine the transfer function of this second order system. Then you get a question like, if you look back in any of the final year exam papers, you will see examples like this. All right, so we're actually applying all these fundamental principles that we have gone through, as well as the derivations of YT, to figure out all these things. How do you determine where is 0.632? Okay, that comes back to the theory that we learned. Okay, in the theory that we learned, which again comes from here, let me go back here. Okay, where is it? Time constant, where we define time constant. Where did we define time constant? Okay, I think we defined it over here. There. First order system. This was the equation. When t tends towards infinity, it becomes k, because e to the minus infinity is 0. When t equals to tau, all right, you have e to the minus 1. When t equals to tau, we have e to the minus 1. And what is the value of y when t equals to tau? Is 0.632, because 1 minus e to the minus 1 is 0.632. 2. And that's why when t equals to tau, the value here is 0.632 of the final value. Okay, Jiaming? You see, we actually went through all this, but somehow it doesn't get enough. Okay, so now I'm slowing down, and that's the whole purpose of the clinic. You have to ask me what you don't know. I keep encouraging you to do that. All right, so now I hope you understand better what we went through previously on Monday, and that will be so for the next couple of lessons. You know, you have missed so much opportunity to ask me questions. All right, so in a way, I can't figure out what you don't know, like, if you don't ask me. So basically that is what we have covered on Monday, right? All these things that I have just revised, we covered all this on Monday. Yeah, Prof? What is it, Chim? Om? What is it, Om? Yeah. If you need help, you let me know. I'm already giving private tuition to people. Okay. So if you need help and you're shy to ask, please approach me. We will find time to help some of you guys, but you have to help yourself by approaching me. Okay. Question about assignment. Assignment will be given out sometime next week. All right. Yeah. So it's a bit weak lah, huh? Okay. Yeah, a bit weak. Right. So please. Okay. Some of you asked me what was the average mark. The average mark was 18. So a lot of you are actually very weak. The average mark was 18. Yeah, going to end soon. So if you don't come to me, no more time already there. We are already in week 10. Next week is week 11 already. All right. So your exam is in week 15. All right, 30th of April. Okay, please, I will be more than happy to help you. If you want personal coaching, I will be happy to do that. I want all of you to pass. Okay, I want all of you to pass. Yeah. Approximately there, huh? I cannot say that this is the pass mark. I'm just telling you that's the average. The pass mark may be slightly lower than this. All right, I'll be slightly lower than this. Okay, the average was 18. Okay, so quite a number of you are obviously having difficulties. All right, okay, so we still have 4 more weeks. Week 11, 12, 13, 14, 4 more weeks before your exam on the 30th. Okay, 4 to 5 weeks. 4 to 5 weeks. So if you approach me and we give you coaching besides the clinic, at least once a week, I think you can make it. You can make it, because all you need is at least some fundamental knowledge to clear the bar. All right, just some fundamental knowledge. So please come to me. Yeah, as I said, I'm already doing personal coaching. I've already started that for those who have approached me. Okay, and a good time for me to do that is usually at night. Okay, at night, because I know you guys are working during the day. So at night, maybe after dinner, we can have an hour, 2 hours we spend just going through things that you don't understand, you know. All right, please help me to help you. Okay. You can ask question like today. Please, can you go over this again? Is it difficult to ask me that? which is what I've just done. All right. And then as I go through it, you can ask me questions again. All right. You don't have to be that specific, you know. Okay, I'll be more than happy to. You say, okay, I really don't understand chapter 3. Can you go over chapter 3 again? Happy to. Yeah, but if you look at the video, it may still not come across, you see, because of the pace of the lesson. So a lot of you have already mentioned that we are going too fast. Quite a number of you in your, for those who have returned me the survey. Yeah, but we got to start somewhere, huh? Okay. If you there are a lot of things you don't understand, we got to start somewhere. If you tell me, you know, from chapter 2 onwards, like, can you please go over chapter 2 again? No problem. I'll go over chapter 2 again. I will revise like this. Pick up all the essential points. Those are the essential points. All right. We have to do it that way. So then it doesn't get, you know, lecture notes of 30 pages, 30 slides, 40 slides. Now we condense down to 3 slides, three written slides. That's it. That is the essential point. We can do that. No problem. All right, everyone? Huh? So don't be shy. I'll make time for you guys anytime. Yeah, I know a lot of things that you're having difficulty, but we got to start somewhere. We got to start somewhere. Okay. I'm not sure if you have any more questions. If not, I need to finish by 12 because I have something that I need to do. Any other things? When will you start going through past year papers? When we have finished all our content, okay. Next week we will be covering chapter 9. Then we will cover chapter 10 on week 12. All right. So it won't be until after week 12 that we can find time to do past year question. But it's no point for me to do past year question when you don't even understand the fundamental. Okay. But if you are ahead, you can understand, and you want a private session to me, you say, I tried this question, I don't understand, this is what I got. Let me know. I will find time and then we can discuss it. Okay. Yeah, we'll find time. But until we finish all our syllabus, right, it really doesn't make sense to start looking at past year question. Also, even if we have finished our syllabus and you don't understand that, going to the past year question will not help you because you do not know how to start. That's the problem. You see what I'm saying? You have to somehow figure a way how to start tackling the question. When I show you the answer, it may so be obvious. Okay, it may be obvious. But when I'm not there and I don't show you the answer, are you able to come up with the same thought process? That's the thing. You have to at least develop some basic capability in that thought process. All right? Yeah. You don't need to know all the fundamentals. If you want to pass, you just need to know some of the essential fundamentals. I know it's almost impossible for all of you to know and remember everything here. There's quite a lot. I understand that. But what is important is at least you understand some of the essential things. And that's when you, by asking question and me doing a revision if need be with you, we identify. So like today, if you go and review this video again later in your revision, you can see that we actually have condensed everything that we learned on Monday to about 5 sheets. That's it. Yeah, you see, we can do that if you want to. We can do that. All right, but I need to know where you want me to which are the ones that you want me to, you know, recap and condense and look at the essentials. Okay. Yeah, that's right. If you know the essentials and then you know how to use it. Okay. So as I said, On Monday, we will complete chapter 9, okay, plus tutorial, part of the tutorial, okay, chapter 6, tutorial 6, okay. Then on the following Monday will be in week 12, we will then complete all the syllabus, which is chapter 10, and the subsequent tutorial, okay. And then moving forward on week 13, hopefully by that time we will complete all the tutorials, and plus I don't know if we have time to do the past year question, right? If we don't have time, we can do past year questions on the clinics, no problem. So if you need more clinics, I can organize home clinics beyond just the Saturday clinics. In fact, it's not uncommon that we do that. Even in the preparation for the quiz, we had more clinics. All right, so anytime anybody want to attend, they're welcome to attend. I can organize more clinics. Certainly the reading week, Monday night, we can have a clinic, because that slot on reading week, there are no official lessons. So that Monday night, we can do a clinic and we can do past year question there. The following Saturday, we can do another clinic. If during reading week, we want another clinic or 2 more clinic, we will organize it. We will do more. Yeah, not a problem. Okay. Yeah, so I really hope that you will ask me to do things, and I can do it in any different approach. So today is like the revision. So if you want me to do a revision, tell me earlier. You know, just now we wasted 10 minutes waiting for the first response to come in. Huh? No point in wasting time like that. Huh? Okay. All right. So let me come to a close today for today. Again, do reach out to me if you need extra help. I'll be more than happy to do that. Okay, as I said, I want you to pass. I don't want you to fail. I want you to pass. Okay, do reach out to me if you need extra help. Okay, as I said, I'm already providing personal coaching to people. All right, so it's just scheduling, that's all. Yeah, email, send me an email. Don't be shy. You can send me an email, you can send me a WhatsApp. You say, I need help. Can we go through this? Can we find a time to go through this again? Can you explain again what are the essential parts regarding this matter? I'm more than happy to, no issue. All right. Okay. So please help me to help you. All right. And then I'll see you on Monday then. Okay. All right. Let me stop sharing. Okay. Have a good weekend, everybody. Bye.